to this interactive session for NPTEL GATE series. Today's topic is soil mechanics, and we'll take over from wherever we left last week. Before that, there is a question in the forum. We'll try to solve that. We have an undefined web section. Let me copy paste the image. We have an undefined web section fabricated from a 10 mm thick plate by fillet welding. The yield stress of the steel is given, and what is the maximum shear load that the section can take. So let us solve this. So the student has asked to solve in as per IS 800 2007. Yeah. So this solution is probably according to IS 800 1984. So as per the new code, we follow the limit states design. And first, let us look at what are the failure modes possible for this. So it is an I section. It is fabricated from 10 mm thick plate. So it is welded together. It is a welded section. So it is not a rolled section. So it is a welded section. And it is usually called a plate gird. Fine. Then what are the modes of failure? So we have to find out the maximum shear load. So what are the different ways it can fail? So the modes of failure are one, it can yield under shear. So one way is shear yielding. That is, if you take the beam, so the beam is something like this. It has flanges. And the web. And in cross section, this is how it looks like. So as you know already, the very purpose of giving an I section is the flanges are positioned far away from the neutral axis. Therefore, the moment of inertia is maximized. So under bending, what happens is that the flanges are much wider than the web. So the contribution to the moment of inertia from the flanges will be something like V times T. If you assume the thickness variation is very small compared to the depth, this is the area of the flange multiplied by, suppose the height of the web is h, it will be h by 4, h by 2 the whole square. This area acts as a concentrated area and is placed at h by 2 from the neutral axis. So this will contribute to bending mainly because this quantity h by 2 is very large and the web will take care of shear. The contribution of the flanges in shear is negligible. Why is that so? Now, if you look at the shear stress distribution in the cross section, it will look something like this. So you know shear stress distribution is given as V cubed by IV from strength of materials. If we try to plot the shear stress distribution, here the shear stress will increase linearly, right? Because the area is kind of increasing linearly. It is Q is what the moment of the area above this point above the neutral axis. And when we just leave the flanges and enter the web, we have a bigger area. So here in the web, this will contribute. And we have a parabolic distribution. So again, here we have a discontinuity. So in the flanges, the width is very large. B of the flanges is very large, say BF. Whereas in the web, it is just TW. So here, if you have, so the this quantity is the same. VQ by I is the same. So here, if you see in the flanges, you have a VQ by I is called the shear flow. That is the same. But there is a discontinuity in the shear stress because here the area that is resisting the shear flow in the flanges is very big, which is BW. Whereas when it BF, whereas when it comes to the web, it is TW, which is much smaller than BF. Therefore, there is a sudden shoot up of the shear stress. So you can most of the time you can neglect the shear stress in the flanges, and you can assume that the entire shear load is carried by the web because this area is much bigger compared to this area. So when you integrate this tau over the depth, you get the shear force. So under the action of this shear stress distribution, you see the maximum stress occurs in the middle around the neutral axis. So when this reaches the shear yield stress, what is the shear yield stress? It is Fy by square root of 3, according to von Mises failure rate. When this reaches the shear yield stress, this point will start getting plastified. So you'll start developing a plastic zone here. And that plastic zone will have zero stiffness, right? So if you see the stress strain diagram of steel, it is idealized like this for the purpose of design. So you have an elastic zone and you have a plastic. So in the plastic region, the stiffness is zero. So when this region yields under shear, this will not contribute to the stiffness. Therefore, it can fail under flexion as this region grows. So that is one mode of failure, which is shear yielding. And the other mode of failure is shear buckling. Now the stresses may be so low that the yield stress under shear may not actually be achieved. But if you consider a panel of the web, it is subjected to shear forces. We can neglect the close to the neutral axis, we can neglect the bending forces, but it is subjected to shear forces like this. And this is the shear flow in the web. Now, if you transform it to some other coordinate, what will it become? This panel is subjected to tension along these two directions and compression in this direction. So a panel under shear is under diagonal compression. So you can see under the action of these compressive forces, this panel can buckle like this. So this panel can buckle in its own plane. So it can take some shape like this, where it is bent out of the plane. So these two are the two modes of failure. And referring to IS 800 2007, it says the factored shear force is given by this. So the factored shear force should be less than or equal to the design strength. So VD is nothing but the nominal shear strength divided by some material safety factor, partial safety factor for the material. And that is 1.1 that you know. When it is governed by yielding, so Vn should be taken as either it should be governed by yielding or it can be governed by buckling. So section 8.4.1 deals with resistance to yielding, whereas section 8.4.2 deals with the resistance to buckling. So this is shear buckling, which I just described here. There it is. Here, this is shear buckling and yielding. This is governed by 8.4.1, 8.4.2. So we take the minimum of the two and design the web. So let us look at it. So let me just write down the equations. So the design shear strength of the web is nothing but Vn by gamma m0, where Vn is the minimum of what is governed by buckling and yielding. So it can be shear yielding or shear buckling. And if you consider the yielding criteria, what does it mean? The stress has reached the yield stress. So Vn is nothing but gamma and Fy into gamma m0 we have already taken out. So this is the yield stress into the area that is contributing. What is the area that is contributing? That we need to see. So area, the web area. So if you see carefully, here it is having a parabolic distribution. So directly multiplying by, so it is a non-uniform distribution. So the true resistance is obtained by integrating the shear stress over the web. but that is too complicated for design purposes. We usually assume a nominal shear area, which is area of the web. And that doesn't cause much issues because stresses are usually redistributed in the plastic range. And AW is given as the thickness of the web multiplied by H, or the thickness of the web multiplied by D, in the case of rolled sections, and thickness of the web multiplied by D in the case of plate girders. Why is that so? In plate girders, so in a plate girder you have a weld here, right? That weld cannot. So the connection here is deformable. Therefore, there is no effective shear transfer between this point to this point. So H is the total height of the beam. So, something like this. So H is the total height, whereas D is the height of the web. So if it is a rolled section, it is monolithic. The entire section is monolithic. There is no connection here. So the entire web, this region, will contribute if it is a rolled section. But since it is a welded section, this connection is kind of deformable. So only this region contributes. So under shear yielding, it is that, and anything else. But there is a catch. So again, so this is Fy by root 3 because of the von Mises criterion. Fy is the yield stress under tension. That. So this and this is under major axis bending. Minor axis, similarly, you have other formulae. Those of them. And when it's subject, when so this is what is governed by yielding. So now you can just substitute the numbers. So here it is. What is Vn? Vn is it is a plate girder, so you should take the web depth, not the total depth. And Fy is given as 250 Newton per mm square. Yielding under shear will have a factor of root 3. Like if you want to know why, I can derive it. And then what is D? D is the depth, which is 300 minus 10 minus 10. So it is 280. And they say the plate thickness is 10 mm. So flanges are 10 mm and the web is also 10 mm. So here it is 10 mm. This is the nominal shear strength of the section. So this is what it is. It is 250, 280, 210 divided by square root of 2. So this is about 404.14 kilonewtons. The design shear strength is just factor it by gamma and Z. So this should be 404.14 divided by 1.2. So this is about 367.4 kilonewtons. So, and as per the so as per the old procedure, what was the answer? Is okay, Fs equal to
300 kilonewtons.
Okay, fine. That is fine because this is according to the working stress method. So this Fs is equal to 0.4 comes, I think it is the factored shear strength, because as per our current codal procedure, it is 1 by root 3, and 1 by root 3 is about 0.57. So I think 0.57. Yeah. So as per the current codal procedure, it is the factor is 1 by root 3 into 1.1, right? And their factor is 0.4. This comes out around 0.52. Whereas this is so as per the working stress, it is more conservative. It predicts a lower value of strength. But as per the current code, it is 367.4. And you have to check, of course, in this case, it is pretty much clear that it is governed by yielding, but you can check the buckling criteria. So the code says you need to design the web under buckling only if d by tw is greater than 67 epsilon, where epsilon is square root of 250 by fy. In this case, fy is equal to 250. Therefore, epsilon is equal to 1. So you just have to check whether d by tw is greater than 67. Right? This comes because, as I said, for this to happen, and it has for this to undergo buckling under diagonal compression, it has to be extremely slender. So this should be a very thin plate. And the limit for that slenderness is something like d by tw is greater than 67. So here d is 280, tw is 10. Therefore, obviously, d by tw is 28, which is much less than 67. Therefore, you don't need to design the web under buckling. But if d by tw exceeds 67 epsilon, then you need to then it means it can undergo right. It is a they have mentioned in the question it doesn't have stiffeners, so it is an unstiffened ice section. So if d by tw is greater than 67, then you need to find out the buckling load, and for finding the buckling load, this portion is there. Typically, this will not appear in gate, but it's a good thing to learn. So the buckling stress, the critical buckling stress of a panel under shear is given by this formula. Right, you can use this formula, multiply by b times t, and then you get the critical buckling load of the web. So this is for unstiffened panels, and if you have stiffened web panels, you have the next section. In this case, it is 300 and what it is 367.4 kilometers. Let's go to the next. That's okay, right? Your doubt is clear.
Yes, sir. Understood, sir.
Yeah. Now let's look at this question. Okay, for some reason it's not copying. Let me take. So we have this. So there is a very simple question. It's a conceptual question, but if you know what these components are, then you will. It's easy to solve the problem. So first, let us look at the behavior of a beam under. So we are looking at a simply supported plate girder. Let us look at what are the failure modes of this beam. So it is simply supported. So you can have, I have drawn the beam itself. So I'm not putting any idealized support. It may be supported on an angle section like this on both sides. And we may have some kind of loading here. We can have some kind of loading here. This angle section may be screwed to some other structure. So it can have some kind of connection here. So these can be columns. And it's now if you see carefully, assuming the load is distributed, so if it is supporting a floor slab, for example, the load will be distributed, and there will be concentrated reactions coming here from the support. So that is one observation. Then if you draw the bending moment diagram of this structure, it is simply supported, so it will be a parabolic. No, it will be WL squared by 8 and all that. So the maximum happens here. The maximum bending moment happens here. And if you draw the shear force diagram, it will look something like this. And this is how you get the shear force. So anyway, the signs don't matter, but here you the maximum occur here. So V max occurs near the support. Now, under some conditions, what happens? So again, for the purpose of design, as I said, how are the bending stresses distributed? The bending stress. So this is the beam. Somewhere, if I draw the bending stress distribution, it will be linear. The top is under compression, the bottom is under tension. So the bending stress distribution is linear. So this is under compression, it's under tension. If the stress distribution is linear, but the area is magnified at the top. So if you look at the force, if the stress so between the web and the flange, the same thing. The flange has a width of df, the web has a width of tw. So if the stress at their junction is say sigma, this will have, and say the ratio is typically greater than 20 or 30. So here the force that is generated will be much larger. So there will be, if you look at the force distribution, there will be a large compressive force at the top flange, large tensile force at the bottom flange, and somewhere in between you have the smooth distribution. So the stress multiplied by this increased weight will give a larger force. Therefore, it is safe to assume that for most purpose of the design, you can assume that it's not just assume, it is the reality that the flanges carry uh, like flanges are responsible for bending, right? Bending forces. Flanges carry the bending forces. And the contribution of the web may be neglected. Because of this, the flange is much wider. So it is the stress here is enhanced. So there's a large compressive force in the flanges. And because you have shifted the forces here, whatever comes to the web is greatly reduced. So the stresses are the same. The stresses are the same both in the flange and the web, but the force carried by the web is significantly reduced. And uh, and if you take the shear distribution as I drew at that time, that has a distribution like this because of the factor of 1 by b in the denominator. The web carries much of the shear force. So it is safe to assume that the shear force is carried by the web. So the shear stress is something like V by what we just did, TW into D. And the bending forces, you can assume they are carried by the flanges. So it is something like, it is compression into the distance of separation, which is about h, roughly. It is not exact, and the compressive force you can find out. So C is equal to, sorry, this is not sigma, this is the moment. So the compressive force is m by the distance of separation. And then you can the compressive stresses are, therefore it is C by the area of the flanges, which is BF into TF. So stresses are not high. So basically the bending forces are taken by the flanges and the shear forces are taken by the web. That is the idea. Now, if you are making a connection in a structure, so a connection is a weak point, right? Now we'll see what flange splices are. Now it is when you have very long span structures, it is not possible to manufacture one long plate. So plates and roll sections come in finite length. So what people do is they take uh, one beam and they take another beam. Because we cannot, suppose the span is something like 30 meters, and the longest rolled sections we have are about 10 meters, then you have to make some connection. So what people do is they put a flange splice here. They put two other plates. I can also put it on the inner side, right, to avoid any unnecessary bending. Okay. And then they bolt it like this. So the problem here, so that what happens? What happens? So the force in the flanges, say, it's under compression. So it's under compression, and this is under tension. The force in the flanges is transferred to the other part by these two plates. So we have put these cover plates, which are called the flange splices. These flange splices will transfer the force. But even in that case, the problem is, suppose you are bolting it, right? If you're bolting it, there's a clearance hole. The bolt will be something like this. There will be a small gap so that you can screw it in. There will be a clearance. The plate, yeah, this is fine. This is the flange, and there is the, yeah. So it is something like this. So the flange is pulled, the plates are pulled this way, and the flange is pulled this way. So what happens? This will come in contact here. This will come in contact here, and before it comes in contact, there's a small slip. Right? There's a small slip. So that actually makes the connection a little weak. So our bending assumptions are not valid here. Whatever the distribution of stresses and all, right, that will get disturbed when we have a connection like this. So when we draw the bending moment diagram, that is assuming that the flexural rigidity and all things like that are constant everywhere. If you have a connection like this, that makes, so one reason is there is no shear transfer between the two. So there is no web in between the two. So these two can move relative to each other. So there is no shear transfer. Therefore, the bending moment capacity is greatly reduced wherever we have a connection. So, so if you have to put a flange splice, you will not. So the maximum bending moment happens in the center. And assuming that the flanges take the maximum, take the bending moment. So C is equal to M by H, or T is equal to M by H. That is the magnitude. So in that case, the flanges are subjected to the maximum tension in the middle. So it is not advisable to put flange splices in the middle of a simply supported beam. Why? As I said, if you put it, there is no shear transfer. It will transfer the force, but there is no shear transfer between the two. It does not make sure that plane sections remain plane and all that. So you cannot use the moment of inertia formula. The bending moment capacity of a connected section is greatly reduced. It starts behaving as two parallel beams or something. So it is not advisable to put a flange splice at the middle of a beam, because this is a critical section. You're designing the beam for the critical, for bending up for this moment. But here, if you put a flange splice, this moment cannot be carried, and therefore there will be a redistribution of the bending moment, and we'll have certain. So if you put a flange splice here, this will not behave as one simply supported beam, because there is some additional flexibility here. It will start behaving as something like this. You put some rotational spring, because there is some additional. It will not become a hinge. It will not become a hinge. It will have some bending capacity, but that will be less than a intact I-beam. Therefore, putting a flange splice at the middle is not, it's not advisable. So flange splice should be provided away from the center of the span, because it is simply supported like that. If you have a fixed beam, you should not put it near the support also, because the fixed beam bending moment diagram is something like this. So flange splices should be provided always close to the points of contraflexion. So these are called the points of contraflexion, where the bending moment is almost zero. So where the bending moment is almost zero, it doesn't matter if you provide a spring or you make it a hinge. So where the bending moment is almost zero, the forces in the flange is very small, so you can connect it by a flange splice. Now coming to the next part, web splice. So where is the so web is critical in resisting the shear force. Where is the shear force maximum? It is maximum at the supports. And there, if you put a web splice, so okay, I didn't say what a web splice is. So web splices, again, you have two beams. Again, you are not able to connect them. Suppose you don't want the transfer of bending moments, right? You're ready to put an internal hinge. If you're okay to put an internal hinge, you can connect these two webs using a cover plate. Same, there is another one on the other side also, right? From the cross section, it looks something like this. So here you have something like this. So therefore, what this does is it will transfer the shear between the two. So this web is subjected to some shear. These two are disconnected. So the connection will transfer the shear. However, the web splice is deformable, right? Web slice is deformable. Therefore, it can allow the beams to slightly slip. So this is also made up of some metal. It is not rigid, right? So what it can do is it can slightly bend like this, and the beams can go little away. So which means you are not simulating a hinge. You are putting a spring like this, some kind of a spring as well. So there is some kind of spring which allows a certain vertical displacement. Again, this means that the shear forces are not transferred effectively. Where are the shear forces? So this is not advisable where the shear forces are large. Shear forces large. So what we should do? We should not put it. We should not put them where.
At the support, sir.
Yeah. Sorry, the presentation was frozen. Yeah, so we should not put them at the support. So web splices should be provided away from the support. Then bearing stiffness, as I said, you might have heard of these already. So there is a constant, so there is distributed force, but that is resisted by two vertical reactions at the support. So what does that mean? If you look at, if you draw the free body, if you draw the diagram, force diagram at the support, this is how the beam cross section looks. And right at the support, you have a concentrated force. A concentrated force, a beam is not designed for concentrated force. At a single point, if you provide this kind of a very large force, what happens is it before if the beam is intact, right? When we do our structural analysis, we assume that the beam is intact. Our moment of inertia is not affected, and but this is also it is also some material. Here you have a concentrated force, and here you have a sudden reduction of the cross section area. So this is the root. This is called the root of the cross section. At the root, the material is particularly the beam is particularly weak. So what can happen is it can locally undergo material failure. This is called web crippling. So here there's a sudden large force coming there. That force needs some distance to distribute. Eventually, because of Saint-Venant effect, Saint-Venant principle, right? As you go away from the load, it doesn't matter how you apply the load actually. So if you apply a force, because there is material, it will eventually get distributed. So away from this point, it will eventually get distributed. But close to this point, the stresses are very high. This is a concentrated force. It's acting on a very small area A. This stress can be higher than the yield stress of the material. So there can be a local material failure, which will cause the web to bend excessively at the root. So this is called web crippling. Alternatively, you can also have, so this entire, as I said, you apply a concentrated force. that will get distributed. So this is the beam that will get distributed. Eventually, it will get distributed, but still it will not distribute throughout the beam. So there will be a region of the web. So this is the side view of the beam. And there will be a region of the web which is subjected to compressive forces. So if you take this panel, this web panel, it will be subjected to compressive forces. And the dispersion may not be large enough so that it prevents buckling of the web. So this under the action of the sudden compressive forces, the concentrated compressive forces experienced at the support, the web may buckle like this. So in both the cases, what people provide, so this is web crippling, this is called web buckling. This is not shear buckling, this is normal buckling. To prevent this, what we provide is you stiffen the web. So if this is the B, if this is a B, and this is the cross section, you know that the thickness of the web is the smallest. Along the length, the web is very long, so it will buckle along its weak axis. This is the weak axis. Now, what stiffener does is it will place a member like this, right? It's a stiffener. This is you can call BS or something. Width of the stiffener. So it means it looks in the side view. It looks like this. So yeah, it is something like this. You provide a member to strengthen the web. Now, if now this has to buckle, it has to bend this stiffener. So this is the stiffener. Yeah. So this is the stiffener. Now, if this web has to buckle, it has to bend the stiffener about its major axis. Right? This has to bend like this about its major axis, and that is not going to happen. So the stiffener will add some. It basically stiffens the web. It cannot buckle easily. So these stiffeners are provided whenever the web is subjected to buckling or crippling, and this happens whenever you have a concentrated force or reaction. Doesn't matter. Reaction is also a force. So wherever you have a concentrated force, you need to provide a stiffener. And that if you see that is that if you see the code, I think it is 8 point. Yeah. Yes, this is stiffener design comes under section 8.7 of the IS code. So there are many types of stiffness. So what I said right now is called bearing stiffener or load bearing stiffener. So that is governed by this buckling resistance of stiffness. That is how you design web stiffeners, these transverse web stiffeners. So again, bearing stiffeners are provided to stiffen the web against web crippling or web buckling. So where should you provide them? Wherever you have concentrated force. Where do you have concentrated force here?
Support, sir.
Yes. So you need to provide this at these supports. The last thing is horizontal stiffeners. So these horizontal stiffeners, as the name says, these are vertical stiffeners, right? Bearing stiffeners are vertical stiffeners. They are provided like this. Horizontal stiffeners are horizontal like this. Now again, when we do all our analysis, when we find the moment capacity, we assume that the section doesn't buckle locally. So local buckling is a very bad mode of failure in which it itself may not lead to the collapse of the beam. But what happens is if you can have a beam like this. It can be subjected to bending moment. So as I said, the top flange is under compression, bottom flange is under tension. If the beam retains its shape, it will achieve its full plastic moment, whatever you call the plastic moment, or elastic moment, whatever it is. But if the top flange is very slender, so this is the top flange. If the top flange is very slender, it cannot take the compressive force, then it will locally buckle like this. And once it locally buckles, so it is like a buckled column. What is the axial capacity of a buckled column? It is zero. It doesn't carry any force, or it carries the critical force. So if you slightly increase the force, it will deform excessively. It is useless for carrying any force. Same thing happens to the top flange. Under compression, it buckles locally. This is local buckling. And once it buckles, you cannot treat the moment capacity as compression into H, where compression is given as BF into TF into sigma Y or whatever. This becomes invalid because it has buckled locally. Locally, once it buckles, this cannot achieve the yield stress. Before even achieving the yield stress, it buckles. Therefore, its capacity is something low. It reduces the moment capacity of the section and it can eventually lead to failure. So to avoid the buckling of the compression flange, people provide stiffener for the compression flange. And those are provided like this. So you can provide a stiffener, you can provide a horizontal stiffener along the compression. Just take a, you have the compression flange like this. The thickness is the weak direction. So just this is the web. So just attach a stiffener like this. Weld something strong so that if the web has to buckle, if the flange has to buckle, it will induce the major axis bending of the stiffener. So the compression flange is stiffened. Now, so horizontal stiffeners are basically this. You provide some stiffener here. So that should be provided in the compression flange, longitudinally somewhere in the compression flange. So these are the correct answers. It's a theoretical question. So
Understood, sir. Thank you,
yeah.
sir.
Okay. So last week we didn't have any students joining us. Uh, would you like to? So did you receive the open channel notes? Was it okay?
Yes, sir. I have studied, sir.
Okay. So you were able to go through because there were some problems. Because I think it's time, so it is difficult to start seepage and this thing now. Again, I think I'll upload the notes. This time I'll upload typed notes probably. That looks better. If you have any doubts in that, because we don't have time, if you have any doubts in that, you can ask. Or I didn't upload the recording still, but last time I solved these problems based on those notes.
Sir,
I can upload
PDF can be uploaded, sir.
the solution of the problems.
Yes, sir. Last class PDF.
Oh, okay. I can upload, but the problem is while solving problems, I don't write in the correct order. So it'll be difficult to understand. What I can do is I can write it in the same way as I wrote the notes, and then that will be better.
Okay, sir.
Is it
But
okay?
even this can be I can able to understand, sir. Even
Okay,
this
fine.
also.
Okay, sure. Yeah, this I can upload right away, and I'll write it neatly, and I can. You had also asked for traffic engineering, right? That also I'll upload.
Okay, sir.
Yeah. So any doubts in the? Uh, if there are no doubts, I can go start and finish some portion, whatever, in 10 minutes for seepage and permeability.
Yes, sir. Uh, C page we can study, sir.
Okay. So let me also open. So this was this thing which I uploaded last time. So if you have any doubts in this, you can ask. It's clear, right? I think there is a mistake that I made in continuity when I wrote equation of continuity. Yeah, this is volume under steady flow. I think this was a small mistake. But anyway, everybody knows that. So this is like the flow rate is equal to the velocity 1 times area 1, so velocity 2 times area 2. Okay. So this I'll correct and I'll upload it again. Otherwise, it was okay. So this was clear, right? If you had any doubts, you can ask. If not, we can get it.
No, sir. No doubts, sir.
Okay. Okay. So let us start seepage today. So basically, this comes under hydraulics of soils. This is called the area is hydraulics of soils, which is the study of the interaction between percolating water and soil. So there are three topics under this. They're all interrelated and very important for GATE. Somehow I don't know, GATE has much higher weightage for geotechnical than geotechnical and soil mechanics than other areas of civil. And it is actually a small like, syllabus is actually limited in this. So there are three ways in which soils interact with the percolating water. One is seepage. This is one class of problems where in dams, you have water on one side. We are interested in how much water is lost due to the permeability of soil, that is seepage. The other is consolidation. So under sustained loading, you have a mass of clay or something. You apply sustained loading, constant load. Slowly, the pores will start closing. The water contained in the pores, which is called the pore water, starts coming out. The pore water pressure decreases, and the soil becomes more and more. The porosity of the soil reduces. Therefore, the shear strength increases. So that is consolidation. And because there is pore water pressure, so there is soil particles, and there are pores. These pores are filled with water. Under saturated conditions, the pores are filled with water. Under an applied loading, the load is taken both by the soil particles and the load is taken by the soil particles. But as the soil particles try to move close to each other under the action of the applied load, the pore water pressure U increases. So there is a certain condition under which the uh, pore water pressure is pushing the soil particles away. So when the pore water pressure increases sufficiently so that the uh, the pressure transmitted between the soil particles vanishes, it becomes unstable. So you have conditions like quicksand, piping failure, liquefaction. Under all these conditions, the pore water pressure exceeds the effective stress of the soil. So this leads to structures overturning, foundations overturning, dams overturning. So this is one aspect. So let us look at the today. Let us look at the equations involved. So these are called hydrodynamic equations. Hydrodynamic equations. So as an open channel flow or in fluid mechanics, the key concept is continuity. What is continuity state? If we have if we consider a mass of soil like this, say dx, dy, dz, x, y, z. If you consider a mass of soil, there will be water entering it from one side, exiting on the other side. Entering here, exiting here, and exiting here. The total volume of water entering this volume of saturated soil. So again, everything we deal with in BTech is saturated soil mechanics. We assume whenever we deal with the interaction between percolating water and the soil, we assume that the soil mass is saturated. That is much easier. In advanced courses, people study unsaturated soil mechanics. That is much harder. But we deal only with saturated soil mechanics. So we have a mass of saturated soil. If the soil mass is saturated, then whatever water is entering that mass has to go out of that mass. You cannot create or destroy mass. So this is basically law of conservation of mass. Now let us suppose you have this mass of soil, and at the center of suppose the velocity vector is v. Now if I take a planar view, let us say I'm viewing from the top. This is dx. So this is the point x comma y. So this will be minus dx by 2. This will be dx by 2. This will be minus dy by 2. This will be ty by 2. Therefore, the total, this is a delta x dx by dy. And out of the plane, we have this. At the center, you have velocity components Vx and Vy. Now, using Taylor expansion, so this is Vx and Vy, which are functions of x comma y. If you take this point, this is x minus dx by 2 comma y. If you take this point, it is x plus dx by 2 comma y. Here it is x comma y minus dy by 2, and here it is x comma y plus dy by 2. And the area of cross section is, if we just look at one direction, let us say what is the volume flow rate along the x direction. So let us call that quantity as qx. What is it equal to? What is the, let us see the volume of water entering from left hand side. So here the velocity along this phase, let us take this phase as AB, ABCD. Qx will be the velocity in the x direction on the face AB into what is the area of the face AB? It is dy into dz. But what is Vx of AB? It is Vx. It is Vx at the center, which is O. Vx at the point O. So it is like Vx of x minus dx by 2, comma y dy dz. But this is nothing but Vx of x comma y minus, using Taylor series, it is partial dv x with respect to x to dx by 2, entire thing multiplied by dy dz. So this is just Vx minus partial Vx by dx, dx by 2, dy dz. So this is the incoming flow. Let us call it qxi. And then what is the outgoing flow? So the outgoing flow is qx out. It will be just the opposite, Vx of x plus dx by 2, comma y, multiplied by the area, which is dy dz. So this is nothing but Vx plus dou Vx by dou x to dx by 2 dy dz. Now, what is the net thing? So Q naught, the outflow minus the inflow is the net water that is leaving the control volume. So this is similar to the control volume in fluid mechanics, but this is a saturated soil mass. It's the same almost. So the net flow, the difference. So this is the so net outgoing. So this is net outgoing water. Net outgoing flow. So this is nothing but so if you subtract Vx gets cancelled, and you're left with del Vx by del x, dx by 2 minus of minus dx by 2 dy dz. So the net outflow in the x direction is partial Vx partial x, dou Vx by dou x. So this is in x direction. Similar in y direction, you have dou Vy with respect to okay, multiplied by this volume dx dy dz. So this is dou Vx dou x dx dy dz, which is nothing but dou Vx dou x dv. So here you have a dv. Similarly, qy is dou Vy dou y dv, and qz is dou Vz dou z dv. So these are the flow in the x, y, and z direction. Now, what is the total? So if the volume of soil mass is dv, and you have also heard of porosity. Let's say n is the porosity. It means you have soil like this. We are fixing a control volume. So control volume is a fixed area in space. It also includes the volume of the pores. And what is in the pores? We are assuming saturated soil mechanics. So the soil is saturated. So the volume of water inside the control volume, inside dv, is what? It is n times dv. Why? The volume of the pores totally. So porosity is nothing but the volume of air by volume of. If it is dry, if it is volume of air by volume of these particles, as the total volume. So if the porosity is n, the volume of the pores is n dV. Therefore, volume of water inside that saturated mass of soil is n times dV. As I said, the control volume dV is fixed. We are not allowing the dx dy dz to change with time. Now the net flow is nothing but qx plus qy plus qz. The net outflow in all three directions. So the net outflow is nothing but dou Vx by dou x, dou V. I'm taking dV commonly out, dou Vz by dou z multiplied by dV. Now dV is constant. This is the net outflow. If there is a net outflow of so much, the volume of water inside the control volume decreases by the same amount. So minus d by dt of, because it is decreasing, I put a minus sign. A porosity into dV is equal to dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z dV. dV is constant, therefore minus d by dt, dn by dt is equal to it's fine. I mean, you know the rest. So now this is the general equation for this is the general continuity equation. This is the most general continuity equation. So this is common for all the three cases that I showed there. Both seep. So this part is common for whether it is seepage or concentration or stability. It has to obey this continuity equation. But most problems in soil. So most problems in soil mechanics, we deal only with steady state seepage. Just a minute. So most problems we deal with steady state seepage. Anything when you say steady state in fluid mechanics, it means fluid mechanics or mechanics in general, it means d by dt is equal to 0. So that is, if you are constructing a dam, you construct an earthen dam like this, there is water on one side, there's nothing on the other side, say tailwater. And there is some kind of pile, say sheet pile. We'll solve such problems. We'll definitely solve such problems. There will be seepage of water because the soil is permeable. There'll be seepage across this. And if the dam is existing for a long time, initially there will be a transience, but ultimately the seepage rate will become steady, will become constant. So this d by dt becomes 0. Therefore, the left hand side of this equation becomes 0, and you are left with the steady state seepage equation in 3D, which is dvx by dx, dvy by dy, plus dvz by dz is equal to 0. This is a steady state seepage equation. Again, this holds always. There is no doubt about this. But how do we determine the velocity? So one thing next part is Darcy's law. But before that, what is Vx? Vx is called the discharge velocity. And discharge velocity is something like the average average rate at which water leaves, right? Average velocity of a section, average velocity through a section. Now, it is not equal to the velocity of water through the pores. Because you see, right, if you're looking at this, so if suppose this is the cross section, the pores occupy a very small volume when compared to the the area. This is suppose this area is dA. The pores occupy a very small volume. And water is actually flowing only through the pores, not through the particles. Therefore, the actual velocity of water through the pores is called the seepage velocity. Called the seepage velocity. And that is much higher than the discharge velocity. What we are looking at is the discharge velocity, which is the average velocity of water through this entire area dA. And that is nothing but the Q, the flow rate. That is, you collect so much water in so much time. That measures that how much water collected in some time. That is the flow rate divided by the total area, the gross area. So this is the discharge velocity, and it is related to. So if you have a difference, if you say you have a sample of water, this side you can provide some head, and this side you can provide. Like, suppose you maintain, you apply inflow, and here you remove water, and you maintain so much pressure head. Like you maintain a certain height, like how we have in the water tanks, and you maintain a certain difference in this height. This is called head level. If this is maintained constant, there will be a constant flow of water through the soil medium. And it is observed that the discharge velocity is proportional to this height difference. So if the difference is very high, the water moves faster. And if the difference is small, it moves slowly. So that we can intuitively expect. And that is what is called as Darcy's law. So the discharge velocity is proportional to uh, the hydraulic gradient. And the constant of proportionality is something called the permeability. So V is equal to Ki. This is the Darcy's law. So K is called the permeability or the hydraulic conductivity. Now, okay, I think it's time. And also my battery is running low. So maybe this is a good place to stop. I'll stop here. I'll upload the notes as usual. I'll also upload some problems for you to solve. If you have any doubts up to this point, I didn't do the last part properly. I was rushing, but we'll do it in detail. We'll do it in detail.
Thank you, sir.
Hello.